Okay, thank you. Next up is Bartal. Højgaard.
Yeah.
You can introduce your.
Yeah. I work at the Faroe Geological Survey, mostly on tunnels, and I'm gonna talk a little bit about what I've been studying swelling clays on the side these last almost 20 years. So what is swelling clay? Yeah, okay. Oh yeah. It's okay. No. That's just hold it. So swelling clays are clay that can absorb water, and while it's absorbing water, it will swell, expand, and this process can be burst and it can expel water and shrink again. Here we see like a lake bed up on the mountainside here in the Tishberg. You can see the clays have dried out, and you get these desiccation tracks. And these, you might also see this in almost microscopic scale in tunnels. If you look like an example, here's a mineral called Montmorillonite, where what's happening is that the rigid silicate sheets are more or less fixed and strong, but they are bonded by like weak bonded by cations like sodium and calcium, and they can absorb water. And the more water molecule it absorbs, the further away these sheets go. There are different ways to inhibit this, like adding something and other things, or pressure. So, how to identify these clay minerals? The proper way would be doing an X-ray diffraction. That's cumbersome and expensive. And I think for dealing with tunnels, we're more interested in to see the effect of it already. We don't need the fancy names. We need to know, does it swell or not? Because there might be swelling clays that do not swell. It's counterintuitive. So a very easy way to check if clay in this fracture here swells is just put it into water and observe it swell. But a more rigorous way to do it is to change water out with ethylene glycol. This was introduced by the U.S. Army Corps in 1949 when they tried to test the durability of aggregates for pavements and concrete. And what the ethylene glycol does differently than the water is the molecules are bigger and they will saturate the swelling. So it will like be foresee what will happen after so many wetting and drying cycles with water. Ethylene glycol will speed up the process. And also, if in this case we have a swelling place within basaltic rock and aggregates in water, nothing will happen immediately. But with the ethylene glycol, as you can see, something happens. This chemical we know from the active ingredient in antifreeze we use in cars, and that's what I use. And for the test method that I've been using is also derived from the and for aggregates, but just like this, just observing over time how severe it disintegrates and how fast. And those two parameters added together on a scale from 1 to 11 will show If it gets a value of 1, then nothing will happen within a month. Or if it has the highest value of 11, then it will totally disintegrate like this easier within a day. And then where do you find these swelling places? And this is important for me to try to predict where to find it before it's doing it all. So here we have a user-nest tunnel just north of Torshavn before the port was installed, and this area here is covered with soil today. And we have some examples of what kind of rocks we deal with on the Faroes. So the top of lava here is up to a place, fairly sheet low, whatever. A very common basalt type, light gray. And below we have all the sandstone and claystone. And cross-cutting the whole thing is intrusive dike. Just all this lava came from some kind of volcano, and you can imagine that this could be a feeder for a volcano that's been eroded away. So to pick apart basaltic units, but that's the only thing that you see in the mountains. We use these small differences, like does it have larger primary crystals of like pluggy clays? Then we say it's these types. It doesn't have the larger crystals, then it's apheric. So a very simple way to distinct the different types. I was inspired by this article. These South Africans that were doing full-face drilled transfer tunnel for water from the Soda to the mainland South Africa, and also the foundation for the Casa Dam. They used this ethylene glycol test, and they came to some conclusions or had observed which kind of basalts were most prone to disintegrate. And on the right side, after the first year at Jarðfeingi, these were my initial results to compare with the South Africans. So we have the South Africans over here. Actually, they only used 18 samples, 18 tests, and I had like 31. Doesn't say anything statistically. But one was hoping to see some kind of, maybe these are stable and the other ones are unstable. The South Africans actually said that these so-called olivine ferric basalts and some of the apheric basalts, they were unstable because of the former has olivine in it, which is relatively unstable on the Earth's crust. It's more stable down in the Earth's mantle, in the deep below us. While some of the apheric basalts that they were testing had originally a lot of glass in the matrix. Glass is like the last part of a lava basalt that cools and has a lot of cracks in them, and it's just basically unstable and will more easily and faster turn into like swelling clays. And so where you take the like solid rock and turn it directly into something soft and what's called it can break down the main rock. So if we jump forward to present day, still that's the old results were biased for few samples. With more samples tested, 400 here, but still also biased because we tend to test rocks that come from troublesome areas in tunnel or rocks that I find suspicious. But in some cases we pick regular intervals, just to get like an overview. Is this a general problem or is this a very specific problem? And we can add more rock types like the sediments into basaltic sediments like claystone and sandstone and the different types of dikes that we have. And they all tend to, I guess, if we were testing enough samples, we would see that the samples that don't react, don't swell at all, it will grow in the proportions to the rest. So that is the larger scale distribution, if there is any difference in different types of basalt. But if you take them more specifically, you'll find a swelling place in these gas bubbles, original gas bubbles within the lavas. You can see the dissipation cracks that you also saw in the lake bed or on the fractures. They can be by groundwater or within the basalt itself, like the mentioned glass just turned over to or altered to clays. Or in more extreme cases, you have a clay soil where you have these clays concentrated. So what is the impact found in tunnels? For scale, we have Denmark, Copenhagen, and Malmö on the right side, and the blue is road tunnels and water transfer tunnels on the pictures. I guess originally we haven't really looked close why things collapse within tunnels. This issue of the Sundbyberg tunnel from the 87 or something. It is a little bit suspicious when this very the senior tunnel person says that they have typically collapses every night after they have blasted. So they didn't dare to try to excavate right after the blast. It was unstable. It could be many reasons, but the latency in time is also something that could be related to swelling clays of some sort, either it's in fractures or clay beds. This sample here is from the Norway subsea tunnel. My colleague Turmas kept it. It was from a problematic interval in the tunnel where it was originally interpreted as rock burst, overpressured rock that just fall off the side, but Turid suspected that it was swelling clays, kept it in a Ziploc plastic bag for a few years, gave it to me, and I put it into this antifreeze and just turned it into mush, just as the same thing that we saw in South Africa in the transfer tunnel, where you see this spalling of. This is from the, so this, you have seen this already. This is the test done regarding to what's called VRI's tunnel or VOI tunnel, VRI's tunnel. Glamour Eliason sitting over there, he took this picture, I guess, and the entire research, the stuff looks nice and all of that, it just crumbles down. And why is this? And I think it was tested at Sintef, Norway, I guess, and also with ethylene glycol, and both tests showed, well, there's swelling clay present. So this is the irritating but not super dangerous impact. It just crumbles off the side of the wall. So we're jumping to this asteroid subsea tunnel, 8th of May in 2018. So the excavation team up here in the left corner encounters a dike that wasn't really specified on the map. It could be found on land, but we didn't extend it to the tunnel because it could be over there. It's a little bit difficult to say. And Yeah, there is sound on this, but in fact, the tunnel hardly get over it will already. So the wall behind there is actually this dike that has been partially altered to green and white swelling place. So took some samples, put into this antifreeze, and so, and the same thing happened to the Sandy tunnel, subsea tunnel, where they encountered two dikes. Both of them were kind of severely altered, like the one in X-ray subsea tunnel. But there's sometimes you will expect some latency, so you might go through an area you don't think is problematic because it's stable right now, and you encounter something else and then collapses, and then you go back and say, well, maybe this will also collapse in time. Anyway, so to more severe cases, I guess, we have swelling clays in valley soils. So in this case, we have like a non-swelling clays and swelling clays, and the distribution of that is completely chaotic, and so it can be difficult to assess how bad the situation is. But the problem in this case was maybe more of the what you say, the original prognosis wasn't good or wasn't accurate enough. We missed these two faults in the prognosis. The original prognosis was only arrived from these the boreholes that stayed open, didn't collapse, that went down to the tunnel level. This one came later. And what we are, oh yeah, just take the next slide. So what is happening over here is that this fault, yeah. So one of the prognosis was that, original prognosis was that I expected the clay horizon here to hit the horizon over here. And we say it's the same at bar here was involved on putting the right level of the tunnel. Well, when they excavated, they just told, well, this we are not out of the clay horizon, and suddenly they encountered this fault, and then everything makes sense, and it's just disappeared, and it comes back up again, and the same thing repeats, but in this area here we have an extra clay horizon which is locally much thicker and also really severely affected by swelling clays, and it was actually exposed in the roof when they got through carefully the fault zone, and they continued excavating, securing, and I guess it was a weekend or something. At least there was nobody present when all of this part here collapsed, and it collapsed up to the upper boundary of this clay dome. So the basaltic wedge that was below. So what was the cause of the collapse? Who knows? But I would say that the clay on top of it was definitely not a strong link in this case. And also, it has some special qualities. Here we find a similar clay bed in the Portuguese quarry, some just what is east of the tunnel, where we find this shiny, bright native copper leaf. These are 55 million years old. So they have never seen a droplet of water, I guess. And the tunnel people that worked on the Pamian tunnel said, well, we see this cover leaf. We say, how stable is it? Well, it's still there until it collapses. I don't have a video of this, but this is the most extreme case that we have seen. We actually put some of this into a glass of water, and it just spits out a whole piece out of the water color, out of the glass. It crumbles very fast and turns from this red color to dark ash. There's a swelling clay mineral in there. It's called non-stronite, but other than that, why is it violent? Is it extra? Call it trigon faster? That was a Norwegian suggestion. It might be that case. It might be. Who knows? We were still working on or figuring it out, I guess. Hopefully. And lastly, I want to show this core here and related to the Northern Fjord tunnels, where this was like only 5 days after it has been recovered from the borehole, and I visited the warehouse half a year later. And so this has the only test here is that it's just been stored in the warehouse with shifting water moisture content, and it will these clay minerals swell up and break the core apart. So over time, I've done the same for the Kvalba tunnel, where we're revisiting like 15 years old core to see if they are intact and exactly where the swelling clays are problematic. You'll see more and more fractures. And some spoils, I guess, from this tunnel, which has been completed now, is completed. I don't think so yet, but it is open. The spoils from this tunnel was meant to be used for pavement, and they were tested by Glassware's lab according to Norwegian standards. At least they use LA, what's called it, LA test and Los Angeles test and Microdeval, and held up for those tests, but didn't held up in the reality. And Glassware, along with the University of the Faroe Islands and the Jarðfeingi, had a PhD project that's just starting to see what kind of test actually fits our purposes. And I guess also our climate is not just the rock. I mean, we hear about freezing temperature in Sweden, and who knows what's necessary here. So that is what's going to be. So now we're also going to be testing aggregates, finally. So we can use native aggregates with the competence. And I think this is the last slide. Oh yeah, there's one more, but yeah. I'm trying to inhibit the swelling with putting in some kind of salts. It didn't work. Yeah. Questions?
Thank you. Thank you very much. Maybe something applause? But it's very interesting. We have swelling clays in Iceland, but it's exclusively in our sedimentary rocks between basalt rocks.
It's really lovely to see Icelandic rocks because they are so fresh and Yeah, it's I almost cried. My colleague came with like a pale basalt from Højgaard.
We have the fresh stuff.
Yeah, the fresh stuff. Yeah.
I actually have a piece of rock from a tunnel in Iceland on on the table that when somebody comes to visit, I break a piece of it, put it in a glass, and it cracks up.
Yeah.
So that's
Yeah.
okay.
Yeah. For testing aggregates, I think maybe Iceland are doing differently, like the UK, where at least introduce some kind of water absorption test, because it's not only swelling plates that are an issue, it might be also the freezing thaw process. So you leave aggregates out in the cold, those that are all porous or microfracture, they will disintegrate. And salt can also be a problem, but maybe less so.
Are there any more comments or questions to Basalt? No? I think our formal program is over. We'll gather for lunch and what's the name of it again? Katrina Christensen. Thank you for coming. And the presenters, thank you for very good presentations. The time working group will have a meeting again here. We'll meet at 1 o'clock after lunch. So the others, thank you. And let's have something to eat. Thank you.